Okay, here we are. This is your last unit of calculus for the semester. We're going to be covering the topic of optimization. This is an absolute must. Okay, it's an absolute must. We also have referred to l'hôpitals rule. Sure, everybody always says little hospital. It's not little hospital, but it's l'hôpital. Have to cover these two. Have to cover Newton's method. Okay. Economics applications really depends on what kind of time we have. So I'll put an open circle there. We just don't know for sure. So very possible that tomorrow we would have a, no school, right? An e-learning day. It's possible that that could happen. So your e-learning assignment would be to work on what I give you today. Okay? We're not going to try to learn this at a distance. But because of that, we're going to try to cover a fair amount of material today. See what I'm saying? So if you don't like the fact we're covering a decent amount of material today, then I would just have to put it into tomorrow's e-learning day, which we don't want that, right? Okay. So again, we're in the topic of applications of derivatives. The first key point that you saw for applications of derivatives are these curve sketching pieces. And hopefully some of you were able to connect with that and say, hey, it's pretty cool that we were able to sketch these curves. The optimization is key, and we're going to look at this example right here. And you'll start to see how this optimization takes place. I will just warn you, here we go. So I love the boxes. They help me organize my work. It says the farmer's making a pen out of 480 yards of fence. Okay? Like Farmer Kendall, right? Kendall has goats, doesn't she? Love the goats. I want to bring my family down to see the goats because we think goats are amazing. I want to like rent her goats so they can like clear up my neighbor's yard behind me. Don't tell my neighbor. So anyway, farmer's making pen, maybe Farmer Kendall for all these goats, he'll be dividing the pen into 3 sections that are all equal in size. And so what we're going to do is we're going to divide these into just 3 rectangles that are all the same size. Why would you want to divide the goats up? Yeah, different breeds. Yeah, you want some to maybe not make baby goats all the time. Yeah, and maybe they're going to kind of consume different parts of the area, right? So because they got to eat. So what dimension should he make the pen to maximize the area? Do you understand that maximizing the area is a good thing? Yeah, that way you have more grass to eat. You got more area for poo, right? Like you want to try to make sure that you have maximum area all the way around. So let's try to make sure we can at least draw a shape. Somebody brought up a point one time that we could make a circular fence. Or a circular pen. This is true. We're going to go with rectangle, okay? I'm going to divide it into 3 sections. So that would be 2 lines would create those 3 sections. That doesn't look very congruent yet, does it? Come on, Gens. That's better. Okay, so I need to understand what's driving this problem. What is the goal? Maximize the area. This is what's driving the problem. You must decide what is driving the problem. So I need a formula for area. Base times height, excellent. I'm going to call it length times width. I will label this one here, length, and I'll label this one up here, length. You all okay with that? So what are you going to label this? Which means this would be width as well, right? So my fencing is made up of 4 sections that are the width and 2 sections that are the length. I want to maximize this area. Now, right now, I have a formula for area, but I have 2 variables. In calculus, we like to work with functions that are written with 1 variable. So what I want is I want to get rid of the L, or I'd like to get rid of the W. what that's going to require is another equation. Okay, so I like this guy. I'm going to use this guy, but to get rid of a variable, I got to set up another equation. Does anybody see some helpful information in here that will help me set up another equation? Yeah, it's 480. So what's equal to 480? 2 of the L's plus 4 of the W's? Okay, let's do it. 2L plus 4, whoop, stop that, plus 4W is equal to 480. So I could solve and have like an L equals or W equals, couldn't I? Do you want to come up with an L equals or W equals? You decide. L. So let's subtract the 4W. I get 2L is equal to 480 minus 4W. Now what? Divide by 2. So I get L is equal to 240 minus 2W. Notice how I came up with the L equals expression. I can now substitute that in for L. So this is where the magic happens. This is the most difficult box for everybody to figure out. That's kind of what it was when we were doing related rates as well, wasn't it? So what I have now is I have an equation. Area is equal to, instead of L, I write 240 minus 2W times W. And if I distribute that W, I have area is equal to 240W minus 2W squared. Somebody describe for me the shape of my equation. Upside down parabola. What is the goal of this problem? To maximize the area. Note that this function is area. We want to find the area at its highest point. I sure wish I knew how to find a local maximum. Take the derivative and set it equal to? Yeah, isn't that great? Look at that. All real world problems. If you want to maximize something or minimize something, it turns out that the maximum or minimum always happens when the derivative is equal to 0. That's pretty nice, isn't it? First of all, we like 0, don't we? Second of all, do we know how to find derivatives? Well, yeah. What's the derivative of that thing? Yeah, 240 minus 4W. It's equal to 0. That's easy. 240 equals 4W. W is 60. What does W represent in our problem? Width. The question is asking to maximize the area, but it's asking us to find the dimensions. So it's not actually asking for the actual area. It's asking for the dimensions. So the width is going to be equal to 60. Is there something up here that tells me L equals so I could find the length? Yeah, in my previous work, I have L is equal to this. So when I plug 60 into 240 minus 2W, 2 times 60 is, and 240 minus 120, now, the point that I would like to make with you is, suppose it asks for the actual area. What would you do? Good, you take 60 times 120, okay? And you get that, great, yada, yada, who cares? So here's what I want you to also understand. People wonder what would happen if you plug 60 back into this equation. It would give you the maximum area. Watch. I have 240 times 60. Thank you. Yeah. And then I minus 2 times 60 squared. See that? This produces the area, or you could find the length and produce the area. Get the point? Now, having seen that kind of a problem, could you follow on in your notes and do a problem very similar to it? Good. That's our goal, is to show you a few of these types of problems that, again, are applicable to the real world. Let's flip it over. Let's try the next one. Yes, so I did not write a final answer. It would be 60 by 120. Yes, Dr. Khan. Stop laughing. Yeah, Mace Dog. I call him Mace Dog. I don't know what you call him, but. All right, so the next one, I'm going to find a set of notes and give it to Leon. Farmer's building a fence against the barn, but this time, since it's against the barn, he doesn't need fencing against the barn. Get my point? So I'll just draw the picture. So therefore, like we've got length, but we've got 2 widths, but just 1 length. See that? Go. Very similar to the last problem. See what you can come up with. Okay, let's glance on up here and make sure we're on the same page. Turns out that the width should be 80. Anybody come up with width 80? I just want to make sure that we understand this right now. Notice how there's 2 equations. People wonder which one to focus on. That's the one you focus on. This is the primary equation. We just use the secondary to help us out to get one variable. You understand that? Because like some people try to like change things around and plug something into here. You always want to focus on this one. That's your objective. Okay? So once you solve, you notice you have the 320. You just have 1 length plus 2w. Subtract the 2w over 320 minus the 2w. Once again, when we plug that in, you get a nice parabola. Set the derivative of 320w minus 2w squared. That is 320 minus 4w. So the width is 80. Okay, great. So I've got width 80. How do I figure out the length? This thing right here tells me the length. The length is 320 minus 2 times 80 would be 160, so I get 160. So the answer is what dimensions? I suppose we would say 80 feet by 160 feet. So whatever you come up with might be part of your answer, or it might be just the way to come up with your answer. Question?
So I got the same answer, but when I did the area, I did like 1/2 the length.
That's fine. So what you came up with here is length is equal to 160. Yep. So you can solve for L or you can solve for W. Either way is up to you. Since the L was by itself, that's why I chose to subtract the 2W. Question? No, you don't have to, but in these situations, I've given you a parabola. Other times, you might have a graph that you don't really know what it looks like. And understanding, so for example, Suppose that your graph looked like this. Well, then it depends on whether or not you're asking for the maximum or the minimum, right? Because there's two spots where the derivative is equal to 0. And then you have to think through that, which is what our next problem is. Here's a demonstration. Here we go. Box with an open top is be constructed to form a rectangular piece of cardboard, or from a rectangular piece of cardboard with dimensions 10 by 18. So this is 18 by 10. And what are we going to do? We are going to cut squares from each corner. I don't know the size of the cut. It says simply find the largest volume the box can have. So volume is what's driving my problem. How do we determine volume of a shape like this? Length times width times height. The area of the base times the height will do length times width times height. Everybody good? Okay, so I got length times width times height. Sweet. Oh boy, I got 3 variables. That's no bueno. I got to get down to 1 variable. I've got 3. This is a big problem. We'll say that we're going to cut x by x, x by x, x by x, x by x. So my box, its length, the longest dimension, is that going to be 18, more than 18, or less than 18? Why is it going to be less? Because you're cutting something off. How much are you cutting off? Oh, length is 18 minus 2x. What's the width? 10 minus 2x. What's the height? X. Is that cool? Sweet. Because when you tip it up, when you tip the side up, it's whatever dimension you cut. You see that? Good. It's important everybody sees that. Okay, so I've got, then volume is equal to the length, which is 18 minus 2x times 10 minus 2x times x. All right, I've got an equation. So volume is equal to, let's multiply these out, and then we'll multiply by an x. So I'll start with 18 times 10, so 180x. And I've got negative 2 times 10 and negative 2 times 18. Okay, so Colin says negative 20 and negative 36 makes negative 56. Negative 56x squared. And then negative 2x times negative 2x, 4x cubed. Okay, sweet. So shape. Yeah, right side up or upside down? Good. Yep, you guys got it. So how many times is the derivative equal to 0? Twice. So are we going to look for the lower x value or the higher x value? Look, everybody. Look. We have x1 and x2. Do you want x1 or x2? We want to maximize the volume, right? So x1 is going to give us the maximum volume. x2 is going to give us the minimum volume. See? So let's figure it out. First let's take the derivative and set it equal to 0. 0 equals, what is the derivative of this guy? Ooh, second degree. How do I solve that? Factor, you just use the quadratic formula, right? Like, I know this guy who really wrote a really cool program for the calculator. Just execute the quadratic formula. Oh, we need, all right, gotcha. All right, yep. Remind me. All right, so A is 12. B is negative 112. And C is 180. And I get 7.27 and 2.06. So 2.06 and 7.27. So do you understand? I was wondering, do you want the smaller one or the bigger one? You want the smaller one in the situation because it produces the maximum? See what I'm... What? Okay, let me try again. What's the goal of the problem? Largest volume. Do you agree that that's going to be the largest volume and that's the smallest?
Yeah.
That's why we want that one. Now watch what happens. Let's say if you use the second one, you use 7. Think about this for a second. Suppose that x was 7. Could you cut 7 off of this side and 7 off of that side? No. You would get a negative dimension, wouldn't you? Yeah. See that? It doesn't even work in the problem. But 2.60 or 2.06 does. So 2.06 is what we should cut. Is that what the problem is asking for? What's the problem asking us to actually find? How do we, given this, how do we find the volume? Plug it back into this, right? So V of 2.06 is equal to, let's plug that back in. So 180 parentheses 2.06. Minus 56 times 2.06 squared plus 4 times 2.06 raised to the third. 168.13. So you can fit 168 cubic inches in there. That's good news. That's helpful for a business who's producing cardboard boxes. Okay, let's pause there. Take out your homework. Okay, so for people watching the video that might, I don't know, Taylor, maybe you're watching it, something like that, on your homework, I'm going to tell you to try problems on numbers 1 and 2, and then try 4, but it might be tough. 3 sets up similar, but we got to try another problem before you actually try it. So 1, 2, and then try 4. If you get 4, then go ahead and do 3.